Outline the mechanism that occurs in reaction 1, include curly arrows, relevant dipoles, and the name of the mechanism. So watch out for instructions like this. They're giving you lots of things you need to include, and there will be marks for every single bit. Okay, so reaction 1 is the reaction of the HBr with the alkene. All right, so we put the molecule back in as it looked, C6H5, carboxylic acid, and we had the alkene there, the double bond there, reacting with hydrogen bromide. So this molecule is polar, this is your electrophile. The bromine is more electronegative than the hydrogen, so put your dipoles on, delta minus, delta plus, easy to make mistakes. Okay, and think again, electrophile then is an electron pair acceptor. So the electrons from the double bond will be able to be attracted to and therefore transfer to the hydrogen of the HBr molecule. So you need a curly arrow coming out of the double bond to make sure it's out of the bond and onto the hydrogen, showing a transfer of electrons here, and the hydrogen able to bond, will start to form a bond with the main molecule, and electrons will transfer from the bond between the H and the Br over to the bromine, allowing this bond to break and forming a bromide ion. Okay, so this means we get an intermediate molecule, a halfway point of this mechanism. 1, 2, 3, double bond O, OH. Still got a C6H5. The single bond is now gone. Sorry, the double bond is now gone to be replaced with a single bond. If you're doing it in skeletal form, you don't need to show the hydrogen. If you're doing it in displayed, obviously you do, but the hydrogen obviously isn't included. So we can now imagine that this hydrogen is now bonded on here. Right, remember the bromine had to go on this carbon because of the roots on the previous question. You would get error carried forward marks if you did it wrong on the previous question, so don't panic. All right, so the bromine then is going to be trying to attract this one, so your positive charge for your carbocation will be going on this carbon here, because that's where the bromine is going to be going. The hydrogen's gone here, so your bromide ion has got its lone pair of electrons. They will now transfer onto that positive carbon, okay? And your final product is in the previous question. I don't need to draw it. That's the main part of the mechanism, and this is, if you remember, electrophilic addition. Okay, compound B, shown below, can be used to synthesize organic compounds with different functional groups. The structure of compound F is shown below. What is the empirical form of compound F? This looks a bit weird because I've chopped a bit of the question out. I've just focused on bits that we were looking at in lessons. So that's why you've got these two compounds very close together. So don't worry about the structure of the question. I've kind of chopped a little bit out of it. So the compound F here, what's the empirical formula of compound F? Empirical form, nice and easy. Count up the atoms and simplify it down to its smallest ratio. So we've got 1, 2, 3, 4 carbons. There's 2 oxygens. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 hydrogens. Simplify it all down. Empirical formula in its simplest form will be C2H5O. Okay, so count them all up and divide them by 2. Right, part 2. A student plans a two-stage synthesis for preparing compound F from compound B. The synthesis first prepares compound E, as shown in the flowchart, which should be on the next page. Draw the structures of compound E in the box and state the reagents for each stage on the dotted lines. So here is the flowchart. So we can see compound B, we've got an alkene, and we're trying to go through a two-stage process to turn that into a di-substituted alcohol. So this is where you've got to try and think of your synthesis as the synthesis routes on the whole. You've got to piece together the puzzle. You've got to think of how can I get from alkene to something, and that's something to alcohol. So thinking about the different ways you can produce alcohols. Okay, well we know that alcohol can be made from the nucleophilic substitution using haloalkanes. Okay, so could this be a haloalkane? Well, yes, it certainly could, because I could react this with a halogen, and that would then break the double bond and put a halogen on each carbon, which could then be substituted to give me my OH. These sorts of things will come with practice. The more you look at your synthesis routes, the more you learn the links between all the different functional groups, the quicker you'll be able to see these little links. Okay, so stage 1 here, I need to put a halogen, halogen atom on each of these carbons, which can then substitute for the OHs in stage 2. So you could pick chlorine, you could pick bromine, doesn't really matter. I'll go for bromine. So if I react compound B with bromine, that will break the double bond in the electrophilic addition reaction, give us an alkane, and each of these then would have a bromine on and it would look like that. Okay, you could put the bromines on the bottom, it makes no difference because it's all one chain. Okay, and then here, stage 2, I've got to substitute my OHs for my BRs. So for this one, the reaction here would require sodium hydroxide. Too many lines for my H. Sodium hydroxide, or you could just go for hydroxide ions. Doesn't really matter. You could go for potassium hydroxide if you wanted to. That's absolutely fine.